Hello everyone, welcome to another lab session on digital signal processing using Scilab. So in today's lab, we are going to see how to perform circular convolution using concentric circle method. So in fact, we are going to see two other methods. So there are three ways you can do this circular convolution. The first of which is concentric circle method. The second one is your matrix multiplication method, and the third one is your FFT using your DFT and IDFT formulas. So we'll be seeing all these three as programs. So before we do that, let me just introduce you to circular convolution quickly if you are not familiar with what is circular convolution. So circular convolution is just like linear convolution, right? So it is used between two signals, and it can be considered as a filtering operation. So but why we prefer circular convolution over linear convolution is when your signals are periodic, right? So what happens, what is the property of a periodic signal? It repeats itself over a period of time. So let us say I have a signal 1 2 and that is periodic, right? So now that signal is going to repeat itself again and again. So let me just write it and show it to you in my Scilab. Okay, so let us say I have a periodic signal. Right, so I have a signal 1 2. This is periodic, right? So it's going to repeat itself 1 2 1 2 1 2 1 2. So this is my what a periodic signal looks like. And now I have another signal which is again periodic. So let me say this is my periodic 3 4 3 4 3 4 3 4. Okay, this is again repeating itself. So that is again a periodic signal. And now if I have to do a convolution between these two signals, I don't have to take this entire signal. So the idea for your circular convolution is I just have to use my 1 and 2 and my okay, so I have to use this 1 and 2 and then I just use my 3 and 4. Done. And after I do that, so here if I see I am having 1 2 3 4 5. So I am having 5 cycles or five cycles I am having. So 5 cycles or 5 frequencies, you can say, right? Your frequency is 5. Now what I do is after this convolution, so this convolution output I am doing it 5 times. So I'm just, let us say my convolution output is C1 and C2. I'm just doing, I'll replicate this 5 times if I want to keep it as 5 cycle. Done. So this is the idea. So this is why we need circular convolution for periodic signals. Good. Another question you may ask is, what if I have this 1 2 1 2 1 2 periodicity? All right, fine. And then my second sequence is only one periodic, so it is only 3 3 3 3. So in this case, is it still possible to do? Yes, you can do. So in that case, what the derivation suggests is you take this 1 2 and you take 3 0. So for circular convolution, one of the condition is both your inputs must be of the same length so that you can wrap them circular manner. So in order to keep them to be of same length, you pad zeros. So here let us say your signal is just 1, right? It is a 1 valued signal 3 which is periodic. In order to convolute this with our 1 2 which is a 2 signal periodic, we pad a 0 to the smaller signal. And this is basically how we are going to do the circular convolution, or what is the background about circular convolution and how the circular convolution happens. So these are the 4 steps. So you need to write the first sequence in your anti-clockwise manner. You need to write the second sequence in your clockwise direction. Okay, so the first sequence comes in the outer circle. Your second sequence comes on the inner circle. So which is your first sequence and which is your second sequence, it's totally your call. You can choose any of the two sequences to be an outer or an inner sequence because they are both the same length. It doesn't matter, you'll end up getting the same answer. And then you do the multiplication and addition, you get the first value. Then you shift the inner circle in anti-clockwise. You shift the inner circle in anti-clockwise manner to get the convolution for your second, third and your fourth places. Alright, so this is how you get all the values, and if they are not of the same length, you do the zero padding, so which is something I already told you. So now let me just quickly show you. My outer sequence is written in anti-clockwise. You can see that A, B, C, D, the direction is anti-clockwise, and then for your second sequence I'm writing it in clockwise, 1, 2, 3, 4. So this is important because once you write it in this manner, the things get a lot easier. And then your first convolution output is going to be 1 into A plus 2 into D plus 3 into 4, right? So we'll see an example, and for next, let us say for the next convolution values, that is going to give me my first convolution value. For my next convolution value, I am shifting my inner cycle or the inner sequence 1, 2, 3, 4 by one place to anti-clockwise, right? My anti-clockwise shift is going to give it as 2, 1, 4, 3. You can see it, you can correlate it, right? How I've shifted it. Now this is needed to get my second convolution value, right? So let's now, I'll quickly, so these are all explained in detail in my lectures on theory, DSP theory. So I'll just do this 2, 1, 2, 1 and 1, 2, 3, 4. This is the example that we are going to write the Scilab program today. So let me show you. This is the first value. I am writing my 2, 1, 2, 1 to be my outer sequence, writing it in anti-clockwise manner, and my 1, 2, 3, 4 is written in clockwise direction, and then I get my output as corresponding values. I am multiplying 1 into 2, 1 into 4, right, 2 into 3 and 2 into 1. So each values are multiplying, and then I am writing this values, and then I am doing the shift. I am shifting my inner sequence anti-clockwise, then I get my second convolution value, and I repeat the shifting for my third convolution value. I shift again one place anti-clockwise for my inner sequence. So you see the outer sequence is sitting there, it is without changing for all these computations, right? The outer sequence is, you write it once in anti-clockwise direction, there's no change to it. Only your inner sequence is getting shifted anti-clockwise each time, and you get these 4 values. So this is basically your circular convolution for your concentric circle method. So we call this as your concentric circle method. So we are going to write the program for this, and then we are also going to see a little bit about our matrix multiplication, which is very simple. So what I do is, I now compute my circular convolution as a matrix multiplication, and how I do that is, I write one of the sequence. So in this case, I'm going to take my sequence to be 1, 2, 3, 4 as an n by n matrix, as a 4 cross 4 matrix. So how do I write that? You can see I'm writing it in a circular shifting, 1 bit circular shifting or 1 place circular shifting. So my first row is 1, 2, 3, 4. My second row is 4, 1, 2, 3. And my third row is 3, 4, 1, 2. And my fourth row is 2, 3, 4, 1. So I have highlighted in blue how the shifting happens, right? So the last element comes first in each of the rows, and then the other elements shift towards right. So this is how you write your 4 cross 4 matrix, and the n by 1 matrix for the second sequence stays the same. So that is 2, 1, 2, 1, and then I do the matrix multiplication. Then I get my output as 14, 16, 14, 16. And now my circular convolution as a DFT multiplication. It is the third way of doing your circular convolution, and this is based on this property of your Fourier transform, which states that your convolution in time domain is equivalent to multiplication in frequency domain. So that is one of the famous properties of Fourier, if you have studied it, and that using that property I can write the circular convolution to be my multiplication of my Fourier, or my multiplication of my DFT. So you can see my first sequence is x1 of n and my second sequence is x2. What I do is, I multiply my DFTs. I take the DFT of my first sequence, I take the DFT means my Fourier transform, discrete Fourier transform. I take those DFTs and then I multiply them, then I apply the inverse DFT to this multiplied Fourier transform. To the overall multiplied, I apply my IDFT, and that's going to give me my circular convolution output, right? So we are going to see the programs for all three of this, and the last one will be using direct functions from Scilab, but the first two will be writing the programs from scratch. So let's get to it. So circular convolution using concentric circle method. So these are the two sequences I'm having. X of n is equal to 1, 2, 3, 4 and my h of n is equal to 2, 1, 2, 1. Just the example I used to show the working of this convolutions. So now what I have, my first line is MATLAB underscore flip LR. So this is a function in Scilab that does my anti-clockwise rotation. So what is the first step? I have to write this 1, 2, 3, 4 in anti-clockwise manner, and that is being done by this beautiful function here. So let me just do these two functions here and show it to you. So what I get here, what is my xn? Now my xn is 4, 3, 2, 1. So I have flipped my sequence in anti-clockwise manner. Alright, so 4, 3, 2, 1 is my sequence, which is now in anti-clockwise manner. I can use this. So this is my anti-clockwise rotation. So now I have my h of n to be 2, 1, 2, 1. Now I'm going to do the first circular convolution. So how I'm gonna do that is I'm going to start. So there I was not doing the cyclic shift, right? I didn't do any shift for the first, I did it only for the second. But in your program we are starting the cyclic shift from the first itself, because that is what I am, that is what is mapping to my function output in MATLAB. So what we are going to do is we are going to see this code and then execute this code, and then we get the output, and then we are going to map this output to our circular convolution function, which is inbuilt function in MATLAB, and then we are going to see whether these outputs are matching each other. Good. So this is my cyclic shift. How do I write my cyclic shift is in this manner. So what happens here is, for my first circular convolution, I'm taking my x of 1, which is already flipped in anti-clockwise rotation. So so I'm keeping my 2, 1, 2, 1 to be my outer sequence. Alright, 2, 1, 2, 1 because I have to shift this. I'm not doing this because it's already symmetric. So let this be as it is. I have already flipped this, and now I'm writing it as 4, 3, 2, 1. Right, how 4, 3, 2, 1? You just see here. Four, 3, 2, 1. Good. So when I do this, I'm going to use it as 4, 3, 2, 1. So my 4 is going. So now this is 4, 3, 2, 1, right? So if I write 4, 3, 2, 1 here, you can see this is my 4, 3, 2, 1, 4, 3, 2, 1. That will map my first, see, 4, 3, 2, 1. Yes, so it is matching here, right? 4, 1, 2, 2. So this is what it means. So that is why I'm doing that flipping. So that one of which, when I do this flipping, what do I mean is one is in clockwise and the other one is in anti-clockwise. That is the significance. That is what circular convolution is intended to do. Now the cyclic shift means I'm taking the last element. So this dollar represents the last value of my x of n, and then I'm putting it here, and then the other values are getting shifted, right? So when I do this, when I do my x of 1 to my x of n, what do I get? So let me see my x of 1. See, I'm getting 1, 4, 3, 2, which means my 1 here is pushed to front. So the last element is 1. That is now placed in the first position, and the other 3 elements are as it is. So my 4, 3, 2 are kept as it is. My 1 is coming here. So this is my first convolution, and h of n is the same. And now I am taking the multiplication. So I am multiplying x1 into h1. Then I am taking the sum, and that is my first convolution value. So I shift this for the second convolution. What I do my shift one more time. So for my x of 2, I am shifting x1. I am not shifting. See, here I am shifting the original sequence. Here I am shifting my x1 by one place. Then I get my second circular convolution, my third, and my fourth. Alright, so this is my YCC4, and when I do all this, I get my full 4 values. So shift 1, shift, every time you keep shifting this and then you multiply and you add. So I can show you one more. Let me take this x of 2 here just to be clear. X of 2 is this. So what is my x of 2? I will rightly guess my x of 2 to be 2143. If I type it, see, you are getting it as 2143. Good. So now what I did was I did 4 convolution values, because this is a 4-point sequence and you are getting 4 convolution values. But it is not an efficient code, right? Well, why it is not an efficient code? Because I feel like a lot of repetitions in the statements. Good. A lot of the same things happening 4 times. So what I can do is I can generalize this using a for loop. I can make it a much compact. I can make it just a 4-line coder using my for loop. And how do I do that is in this manner. So I overwrite it. Every time I'm overwriting my x of 1, so that the shifts are happening and it is storing in the same variable, and then I'm putting a loop for I is equal to 1 is to how many convolution I'm having 4. Now this can be extended to any values. So what I did here 4 times, I've just put a for I equal to 1 to 4 and then put all these 3 statements in one loop. And then that is your circular convolution using Scilab. Hope it's clear. I'm getting the answers as 14, 16, 14, 16. Now let me go to my MATLAB. Yes, see, this is the MATLAB function for my circular convolution and I'm getting it as 14, 16, 14, 16. Good. Let's change the value 1, 2, 3, 4. Let me make it as 5, 6, 7, 8, 5, 6, 7, 8. Let's run this program and see what is my output. 66, 68, 66, 60. And let me go to my MATLAB, and what did I change? I changed my H. So let me do the same thing here. 5, 6, 7, 8. And then I am doing this 66, 68, 66, 60. Is it matching? Yes. Let's get to the next program. Okay, so now let's see the next program, which is our matrix circular convolution using matrix multiplication and your matrix multiplication and this one. What is that? Fourier transform method. So I am using the same sequence 1, 2, 3, 4 and 2, 1, 2, 1. So your matrix computation method is pretty simple. So FFT of x of n is equal to this. Good. So what is happening is I'm taking the FFT of my input sequence x of n. I am taking the FFT of h of n, and then I am taking the inverse FFT, which is my comma 1. Right, and then I do that, I'll be getting this output. So I'll be getting the output 14, 16, 14, 16. So minus 1 is for forward and plus 1 is for inverse FFT. So my argument of plus 1. So the default is forward, and if I give it as plus 1 here, this is going to do my IFFT. Alright, so that is for your FFT method. And now the third method was my matrix multiplication, where I need to write a circular shifted and stacked matrix. So I am doing my circular shifting and stacking, right? I'm stacking into a matrix. So what is happening here is I am, let me just go here. I need to write the matrix in this manner, right? So I need to write this matrix, and that I am doing it here. So what basically I am doing here is, if you see the program, I am taking my x of n is 1, 2, 3, 4, and that is going to be my first row. All right, and then I'm stacking with x. So every time I'm stacking my x of 1 to this matrix. So what is happening here is, first I'll be taking this x of 1, right? So let me just put this for n is equal to 1 to, I'm just going to show it to you, 1 into 2. So I'll just do it for 2 iterations, or let me just do it for 1 iteration, and let us see what is my x1 here. So if you see your x1 is 4 1 2 3. So which means I have shifted it one. I've done circular shifting once. Now if I do it twice and I run it, so my x is now updated as 1 2 3 4 and 4 1 2 3. So what do I see this 1 2 3 4? Because now when it runs the first time, right, the x of n is not shifted. So let us see for 3. This will become very clear when I do it for your third one also. Yes. Now if you see, so your 1 2 3 4 is the original sequence x of n, right, and that is my x1. So the first stacking happens is 1 2 3 4, and then the next one is 4 1 2 3, and again it is 3 4 1 2. Good, 3 is coming here, and then when I put it as 4, I get the fourth stacking, and that is your okay. So now this is the matrix that I want, right? 1 2 3 4 4 1 2 3 3 4 1 2 and 2 3 4 1. So this is the matrix that I want, and then after I have this matrix, what do I do? Is it matching? Now there is a slight mismatch with what I intended to get, right? Let me see this. I wanted it to be 1 2 3. Oh yes, it is matching. Good. So then no problem, because how this is matching is I am using this flip dimension. So if I don't use this statement, right, I'm not going to use this. In that case, let me see my x1. Okay, let me go and see my x1, which is without the flipping. So my x1 is going to be okay. So I'm only doing the x. So x1 is going to have only the latest value. Okay, fine. I'll just remove this for the time being, and let me show you. If I don't do that flip dimension, my x is not going to match. So what is happening is this. What is happening is 1 2 3 4 is the first row, and then the second row is put. It's appended to 4 1 2 3. It's appended to top of that, and then the third row is appended to the top and fourth row. So the stacking is happening at top to bottom, right? So it is doing it in this manner. And that is one of the reasons I am doing this flip dimension. I could have easily put this as x. You could have asked me why. What if I put this as x colon x1? If I do this, will that take care of the issue? So let us see what happens in Scilab. So when I do that, and now my x is, see, 1 2 3 4 4 1 2 3 3 4 1 2. So it takes care of the issues, right? So it is the same thing. I have done it, right? So I can do it in this manner also, but I just wanted to introduce that flip dimension. So I have put it in this manner, and then I've used this flip dimension. It is very useful in other programs also. We'll be using this a lot. So the flip dimension flips our matrix on the row basis, and you get this value. So after I apply the flip dimension, I get the values 1 2 3 4 4 1 2 3, and this is what I do. I multiply this. I take my h of n transpose, that is going to be this 2 1 2 1. So h of 1 transpose is this 2 1 2 1, and then I multiply it, and then I get my convolution. Alright, so this is how I do my circular convolution in matrix multiplication. YCC will be again 14 16 14 16. Good. Hope these two programs are clear for you, right? How do I do this program on 1 2 3 4 5 6 7 8? Why do that, and how do I measure the values? Excellent. So that should be good.